I was digging through some old CAD files and I came across this design I made way back in 2014. Now at the time, I knew almost nothing about engineering. Well, even today I'm entirely self-taught. But looking through the lens of experience, I can see there are several things that I would have done differently had I made this clock today. For example, the planetary gear in the back actually drags against that wall as the clock is spinning. Not only is that going to produce a lot of noise, but that's increasing the friction, making the clock work harder. That's one of the things that I intend to change about this clock. Despite all of its flaws, I still think this design is very beautiful, and I would love to bring this thing to life. So I decided this would be a great opportunity to teach you guys a little bit about how gears work, and then also bring you along on this journey as I bring this clock to life. Let's get started. Before we start building the clock, let's talk a little bit about gears. Now, when I wanted to explain this concept to my kids, I basically built the most ghetto seesaw you've ever seen, and we just experimented with it. If you've ever been on a seesaw, then you know what it's like to sit opposite of someone who doesn't weigh the same amount that you do. You intuitively shift your body weight forward and back to try to balance out your weights. But what you're actually doing is balancing out the torques. Torque is a combination of the force being applied to the lever times the distance from the center of rotation. In this example, you can see my kids quickly figured out that if you have twice as many bricks, then the lever needs to be about half as long. The same thing is true with any sort of lever. And now I want you to think about each tooth on the gear as being an individual lever. Since the motor connected to this gear has a fixed amount of torque, increasing the length of the lever means you decrease the amount of force that can be applied at the end in order to balance the equation. The same thing is true for all forms of mechanical advantage, including pulleys. Looking at this pulley, for example, the center of rotation to the groove is the length of our lever. The motor itself has a fixed amount of torque. Therefore, in this case, we take the motor's torque divided by the length of our lever, and that's how much force we can apply to the belt. So let me give you a pop quiz. If we put this pulley on the motor instead of this pulley, what do you think is going to happen? Hopefully you're saying to yourself, you should get way more force output on the belt for this one than this one. And you will be correct. The force that you can apply on this pulley with the same motor is going to be way higher. But there's an interesting trade-off. If you look at the arc length from here to here compared to this one, it's way longer, right? To go a half a rotation on this pulley means the belt will have moved significantly further than with this one. And that's actually the trade-off that you get. Putting this guy on your motor is going to give you much less force, but a great deal more speed. And vice versa for this one. You can put out a lot more force from your motor, but it's going to be a much slower speed. All forms of mechanical advantage have the same secret sauce. Whether you're using gears, pulleys, a block and tackle, you're using a car jack, hydraulics, they all work exactly the same way. The total amount of work being done is always the same. But if you use mechanical advantage, you can get more or less force output by trading how much distance you actually move. Hopefully this will distill one of the very common myths that I run into, where people think that you can just take pulleys or gears and increase the work output. That's not what these things do. There's something being given up with each one of these exchanges. With the block and tackle example, you can lift twice as much weight, but you have to pull twice as much rope through the pulley compared to the distance the load actually moved. Let's make one solid example so you really have this fixed in your mind. We have a GoKart. It can carry 100 pounds and drive at 20 miles per hour. You can make those units whatever you like. This could be 100 kilograms and kilometers per hour, whatever makes you feel good. The key here is gears allow you to trade one for the other. So we can lower our carrying capacity if we want to increase our speed. And this would very likely be feasible with gears. You could cut your towing capacity in half and double your speed. The same works vice versa. We could cut our speed in half and double our towing capacity. But what you cannot do is leave the capacity the same and try to increase the speed with gears. This won't work because you need more power in order to increase the total amount of torque and speed combined. That's the definition of power actually, is speed times torque. Now, we can certainly get the wheels to spin at 40 miles per hour as long as the load is below 50 pounds. But if you try to carry the full 100 pounds, you're not going to get this go-kart to spin. In fact, it's just going to stop dead because there simply isn't enough power available. This kind of system would require a larger motor because you need more power. If you took that same go-kart and you lifted up the back wheels, There's no load on these wheels. They will definitely spin at 40 miles per hour. But as soon as that go-kart touches the ground, it's dead in the water. It's not going to move. This is the trade-off that you're always going to experience with gears. They don't give you more power. They just allow you to trade speed for torque. All right, now that we have that down, let's go back to the clock. What makes the clock such a beautiful example of gears in action is because we need several different components to spin at different rates. And what better way to get those components to spin at different rates than with a series of gears? So let's make this gear our driven gear. If we attach our motor here and we start to spin this gear clockwise, two things are happening. Number one, the output gear is spinning counterclockwise. That's important for our clock. If we want all our hands to spin clockwise, then we need to pay attention to which direction the output gear is spinning. The second thing you should notice is that this gear has a lower RPM. It's spinning about 2/3 the speed of our input gear. And that is directly proportional to the number of teeth. So this gear has 16 teeth and this one has 24. If we switch this around and put the motor on this side, we'll get a higher output speed. In fact, we'll get 1.5 times the speed on this output gear, but we're going to have less torque or less lifting force to move our load. Finally, if you just want to flip the direction of your output gear, you can add one more gear in the series. And I don't have a pin to put that in place, but I'll just hold it like this. And as you can see, even though this one is spinning counterclockwise, any gear attached on the outside, if I could hold it in place, there we go. As you can see, this one is now spinning back clockwise. This is the trick we're going to use to make sure that the output of our clock spins all the hands in the right direction. Now that we see them side by side, hopefully you can start to see the parallels. The major difference between these two is these will both spin in the same direction and these will spin in opposite directions. If this is our driven gear, then one full rotation will not produce one full rotation here, and therefore the output speed is lower. But again, the torque is higher because the length of the lever arm is longer. The same thing is true over here. One full rotation of this pulley means however much belt will go around one full rotation is the same amount that will go around this, and therefore we won't get a full rotation on the output. Lower RPM, but higher torque. There's one more interesting thing that gears will allow you to do, and that is you can vary the output speed within one rotation. Let me show you. Now, you're probably looking at these gears and thinking this won't work, but actually it works quite well. And what's clever about these gears is we're varying the pitch diameter on the gear, which will increase and decrease the speed within one cycle, but they're varying the same amount. If this is our driving gear, you can see the lever is very short here and the speed is really quite high. But as you move around to the other side, the lever is really long and the speed is very low on the output side. Once you start to really understand how gears work and how to design them with a varying pitch, you can make almost anything happen with gears. All right, I think that's enough talking about gears. Let's get started on this clock. My original intent was to design a very attractive looking clock that told time. Since the primary goal was to make a very attractive timekeeping piece, there was a lot of emphasis on making the clock transparent. I've got some acrylic pieces in here. Most of the gears, as you can see, have very large openings, which will allow you to see all the way through the clock. There are also way more gears than you actually need in order to change the 6 RPM of this little microwave motor to the speed needed to get the minute and the hour hand moving at the appropriate speed. One of the first things that I want to do is maintain that original transparency. One of the other goals that I had was to make all the teeth large enough that I could cut all this on a scroll saw. This was before I had a laser cutter or CNC or any kind of tools that would allow me to make very precise gears. I wanted to make sure that the teeth were large enough that I didn't kill myself trying to make each one of these. But I also didn't want to have so many teeth in one gear that if I made a mistake, I'd have to scrap the whole gear and start over. It's one of the problems with making these gears by hand. If you have 96 teeth and you mess up just 2 or 3 of them, you got to start over making those 96 teeth. And that's just awful on the scroll saw. But today I don't have that problem, so I could change these to accommodate a higher number of teeth per gear, but I think the clock looks great the way it does, and so that's not one of the changes I want to make. As I mentioned in the intro, I need to beef up this connection here so that these gears can be cantilevered and not rubbing against this face on the back. I'm going to add a spacer here. Right now, this clock is being driven by a synchronous AC motor. This is the motor you would normally find in a microwave. It's the one that rotates the plate. The spin rate of this motor is very reliable to give you a consistent 6 RPM. I want to remove that and actually put a little stepper motor there and a small electronic setup that will allow this thing to keep time with the stepper motor. As you can see, there's a bearing here, but I don't think we need bearings for this application. The forces and speeds are very slow and very low. I also had what I called a mantle base. I never quite finished it because I never finished the clock as a whole. The final change I want to make is make sure that all of these pieces can be laser cut. I think that just about covers it. So how about we crank up the speed of this video about 6 or 8 times, and you guys can watch a time lapse of me improving this clock. In the original design, I used bearings throughout the clock because, things are spinning, and so I thought you should use bearings. But in reality, the forces and the speed is very low in this clock. So I'm going to be using bushings instead, basically a custom bushing. So this is a brass tube. I've selected this tube and this aluminum tube because the fit is very good between them, so there's no custom machining needed. I specifically picked this size so that I could put an M4 tap in the end of this hole. Now what I need to do is take some measurements here and figure out how to make this a good press fit. If I was gonna be machining the gears, then I would just go to my machinist handbook and figure out what tolerance would give me a press fit. But I'm using a laser cutter and I don't actually know the kerf of my laser cutter. Kerf is the width of material that's being removed whenever you cut something. So on a table saw, the width of the blade is your kerf. In this case, the laser cutter is doing the same thing. Even though it's ultra thin, it is something, and I don't know what that something is. I have made a little test pattern here. We're gonna cut this out on a laser, and let's see what size hole gives me a really good press fit. I'm gonna say that's pretty good. Yep, okay. I glued this up last night and left it clamped, and I unfortunately must have slid this piece at an angle when I was clamping it down, because now the hole is crooked and I need to remake this piece. So I ended up just tearing off these ends so that I could get the little metal pins back out, and we're gonna try to make this again. I've been trying for a couple of hours now to make these little bushings, and you can see some of them need to be really small. It is not working out very well. As you can see, when I'm sawing it, I'm not doing a perfect job of sawing it. I've got that little burr, and that burr, despite my best efforts to clean it up with the deburring tool, is grabbing onto the shaft and making it where either I can't feed it in or I can't get it to rotate inside. Because it's so small, it's really difficult to work on this piece. If I try to grab it with pliers or with a vise or anything like that, I deform it, and then you definitely can't get the shaft to go inside. So I've decided that these little pieces are just not worth the trouble it takes to make them. I'm gonna bail on this and buy myself a store-bought bushing. I'm gonna make the fit loose enough that I can just push in the store-bought bushing and then glue it in place. So that should work out just fine. I actually have a bunch of these here in my shop. I don't think any of these are the right size, but these are examples of bushings that I got out of a copier machine, a printer. This is what we're looking for. Just when I'm about to start running the clock for the first time, my son walks in and I'm instantly hit with a great idea. Why not have my son write the code for me? Not only is he capable of doing it, but I love any excuse to get him involved in my projects. I want a really simple code with a variable at the top that lets me change the RPM. And that should be all I need. And the default should be 6 RPM, but we want to be able to adjust it.
Yeah, definitely will change that easily.
Okay.
So the drivers on your desk too?
Yep, they're both stuck in the same breadboard. This looks like my business as usual face, but I'm super proud right there. I'm here editing the video, and as I reach this part, I realized that this is the best possible time to tell you about my sponsor, Kiwico. Kiwico ships you these crates, which are basically hands-on projects based on STEAM concepts. Now, at my house, we make it a family event. We'll all jump down on the floor and tear into our crates together. However, this last time, my oldest daughter wasn't with us because she actually had to work. Can you believe that? They grow up so fast. Kiwico makes 9 different lines of crates tailored both to the age and the interests of your kid. So this works both for a family setting as well as handing the box to your kid and letting them tinker on their own. But one of my favorite reasons for doing it together is it brings up interesting questions like, what's the difference between a screw and a bolt?
We used to call them screws, now they're bolts. But they're the same thing because they have the same picture.
Is there a difference, Dad, between a screw and a bolt?
That is a hotly debated topic, ma'am.
Ooh, get into it.
And I'm sure if I leave that in the video, there'll be a huge discussion about that in the comment section.
Like, well, actually.
Exactly. So what is the difference between a screw and a bolt? I want to see your answers in the comment section. We've been opening Kiwico boxes for almost 2 years now, and I gotta tell you, we haven't had a single disappointment. So here's the bottom line. You can have awesomeness delivered to your house, to your nieces and nephews, whatever little kid that you love. And you'll be supporting this YouTube channel by going to kiwico.com/fielding50. That's kiwico.com/fielding50 to get 50% off of your first month's crates. You will not be disappointed. My son's worked on several projects with microcontrollers at this point, so I asked him to put this together for me, and he wrote the code. It's a really simple, basic code. I'll make that downloadable in the description. Oh boy, I feel my heart rate going up. You know, I really should have tested this piece by piece instead of everything at once. I'm not taking it back apart to figure it out, so let's just see what happens. Oh, okay. So just a minor interference. I'm going to need to tinker around with the spacing there and get that offset just a little bit higher. And then hopefully that'll be the only thing that jams. The next several days kind of went like this. I would disassemble the clock, add or remove spacers, reassemble the clock would jam after a few hours, disassemble the clock, rinse, repeat. Watching it like this, it kind of feels like it took a long time, but in reality it only takes about 5 minutes to disassemble the clock. And the only other issue I ran into was some of the gears weren't quite flat enough. So they would run for a while, but there was just enough wobble that they would only jam in some positions. So I ended up recutting a couple of the gears as well. Once I resolved the spacing and flatness issue, I had a working clock. The other good news is while I was literally waiting to see if my clock was going to keep running, I had an opportunity to work on Jarvis. I made some significant progress there, and I'm really excited about sharing that with you guys here in the future. Now that I'm done with the clock and everything's working, I've decided to go ahead and make one huge improvement. I want to design this back plate so that the motor is removable. If I can take this motor out and replace just the section where the motor is, that means I can not only try different types of motors, but I can also disconnect the motor and push all the gears in the train by hand to make sure that everything is working and there's no interference without disassembling the clock and without trying to backdrive the motor as well. Not only is that going to be a huge improvement in 2 categories, but it's a really easy change to make. So I didn't want to let this video close out without giving that a shot. I think we're ready to go. Final test run. It's looking pretty good. I'm really excited about how this turned out. As you can see, in this last test run, we were using a servo motor, which is super overkill for this application. It turned out to be way quieter than a stepper motor. I guess that's not surprising, but you could barely hear the clock at all while it was running. I know some people are going to ask about plans, and the answer is, I'm not sure. So if I ever make plans and you're watching this video a year from now, then just check the description and there may or may not be plans available. I also haven't talked about compound gears, which is what you see me doing here, or how I designed this planetary gear, but I've been editing the video while this was running and I realized that the video is a little bit too long to add that stuff. So I'm gonna put some links in the description to YouTube videos as well as some web pages that will explain in detail how to make a planetary gear with the right number of teeth, the right number of planets, all that good stuff. And also how these compound gears work, how you can use them to make sure you get the right output speed. So I'll be sure you have that information. I won't leave you hanging. One thing that we could do that might be fun is we could change the face to read 6 increments instead of 12. We could double the speed. I mean, I've got precise control over the speed of the motor, and one full rotation could be 6 hours instead of 12. Because all the gears are moving faster, the clock will look a little bit more dynamic. And, you know, who cares if you only can read 6 hours instead of 12 in each rotation? Again, it's meant to be decorative. I guess the last thing I need to do is decide what kind of motor I want to use for its final application and figure out where I can put this thing in the house. Anyway, thanks for watching.